All right. How's everybody doing?
Good.
I think I know most of you guys. Anyway, my name's Bobby James. And we're going to talk a little bit about basic electricity. Probably a lot of you guys already know a lot of this stuff, but I want to go over it just because there's sometimes even most experienced guys have confusions on some of the most basic terms. And I think the best way to get started would be to first, I want to go over a couple of terms. There's a couple of aspects. Probably you guys have heard volts, voltage, you know. And in electrical design or engineering, whatever, we can often equate electrical circuits to hydraulics or pneumatics. In other words, there's currents flowing there too, and it's a little bit easy to understand that. But voltage is, in electrical terms, is pressure. So if you were to equate the electrical circuit, if you were to think of it as like a hydraulic system or a pneumatic, it would be the quantity of pressure, and that would be the potential for current flow. They often call it potential too, electrical potential. We also have, I don't know if this thing's going to write, amperage, which equals flow. And that's the flow of electricity in the line. That's a quantity of actual electrical energy flowing through the line. There's another term we could look into here too. In doing work in this, if you add these things together, you get what we call watts. Actually, multiply them, which is the power, the amount of power. Okay, that is to say, at a certain pressure, given at a certain flow, it'll do so much power. It'll do so much work. You know, you have the capacity for so much work. In other words, say if you had 5 volts at 1 amp, it would do 5 watts. You multiply them together. Multiply volts times amperage, and you get watts. Some electrical components can be equated to water flow in a pipe. This is a basic way to understand how these components function. Okay. I didn't have to write that. What do you guys tell me? Okay, so we got electrical voltage is water pressure. Electrical current is amps, water flow. You also see voltage many times in the symbol they use is often E. And that's just a fancy way of saying pressure. And that's short for electromotive force, which is the electrical pressure that gives you the potential. All right, let's go on to the next thing. Everybody got that? That's pretty simple, basic. Okay, so next thing we're going over is resistor. Resist voltage and restricts current flow. Generally, you'll see this symbol here on electrical diagrams. It'll look like this. And so basically it's resistance to current flow. If you think of it in a pipe, you see the guy there pinching it. A resistor would be as if you were pinching the pipe, and that resists current flow. It also increases the pressure. So you get a voltage in electrical circuits. It creates there'll be a voltage across the resistor because of that pressure. There's a difference in pressure from one side to the other. The same as if you did this. If you pinch this, the supply side, there's going to be more pressure on this side than on that side. Let me draw a quick circuit here. Because there is a formula that goes with this too. Say we have a battery here. And say we have 10 volts. This would be direct current. Batteries create direct current. We'll talk about that a little bit later. It's only flowing in one direction. And there's our little resistor. And we connect, so we'll call this plus, minus. And we have a simple electrical circuit. flows from the battery through this resistor. We'll call this, the units, the resistors are generally given is ohms. And we'll give this a volume of 10 ohms. They also use this symbol like that. It's a little for ohms. I think that's Greek or something. Anyway, so in this circuit, we have 10 volts across 10 ohms. Anybody care to guess how much current would flow through that? 1 amp, right. You get 1 amp of current flow through there. That's because E over R equals I. I is the symbol for current. So we take 10 volts divided by 10 ohms, you get 1 amp. If we were to change that value, you could increase that. Say if we went to 100 ohms, then we'd only have, 1/10 of an amp. So the higher you go in resistance, the less current's flowing across that resistor. Okay, let's go on to the next one. Okay, capacitors. Okay, it's basically a storage for electrical energy. Getting back to our water analogy here, you could have like a battery as being a large water reservoir, and if you put a capacitor across it, it'll be like a smaller tank, and it would fill up to whatever the level of the. So if we were to put our battery back here again, and if you hook up one of these capacitors, that's the symbol for capacitor, and you get 10 volts, then this will charge up to 10 volts to equalize. It's basically two plates separated by an insulator. It acts, once it's stored, it's basically a insulator. Once that's charged, it's insulated. There's no more. In other words, current doesn't flow through there. There's actually no electrical connection. It only flows until the plate is charged. The plates are charged. All right, diode. Basically acts like a valve. That's our symbol for the diode. And it just works like an electrical valve. It only allows current to flow in one direction. You've probably seen one-way valves in hydraulics. Water will only flow through one way. Diode does the same thing electrically. So we want to talk about motors. We want to get into the magnetic component of electricity. Okay, so when current flows through a conductor, a piece of copper wire creates a magnetic field around it, something like an energetic tube around it. It is a magnetic field. And this is what they call the right-hand rule. If you grab the conductor with your finger pointing in the direction of the current flow, the magnetic lines are circling in the direction of your fingers. So if we take that same conductor with that magnetic field and form a coil, then all those lines of force combined creates a magnet. Basically, you make a temporary magnet. In this case, they're just using a nail. If you coil this around, then this will form magnetic lines this way. It'll look just like a magnet, and it forms poles. You get a north pole and a south pole. And one of the characteristics of these are a coil would be called an inductor because it induces electromagnetic field. One of the characteristics of these is each one of these has that magnetic field around it, and once you energize this, it has an overall field. If you disconnect the power, that field collapses. And then as it crosses those metal windings, it induces a current in the other direction. It can be a very large spike. I don't know if anybody have ever done that. Disconnect the coil, make a pretty good arc. One of the uses for those things I was talking about, the diodes earlier, the one-way gates, they'll hook them across here so that they're not conducting normally. It'll be in the closed valve state across here. They would just hook it across here. That way it protects the supply side. When you disconnect this, now it has, since it induces in the opposite direction, it'll flow through the diode instead of whatever you're supplying. They call those flyback diodes. The other thing when you initially, these things resist changes in electrical current. The reason for that is is each one of these conductors, like I said, has its own magnetic field around it. When you change it, it's going to either expand or contract and cross the next guy. And the next guy is resisting that. They push against each other. So it doesn't want to change. And so there's a lag. From the time you make the contact, there's a lag while that thing expands, because it's actually internally pushing back against the current you're applying. And so there's a time lag on how quickly this will actually conduct. Once it's conducting at full, it acts just like a conductor. But while it's charging, it's resistive. They call that inductive reactance. And that's important in a little bit of safety advice here with these guys. And any of you guys ever seen these current transformers? And these are basically coils like we looked at before. If you pass a current through a coil, it'll produce a magnetic field. Conversely, if you pass a magnetic field over a coil, it'll create a voltage. Okay? And that's what these are. These are coils, and these are power lines. And they put these around those so they can pick up current, and these are called current transformers. And they pick up, there's a magnetic field. These being alternating, that magnetic field alternates backwards and forward, alternately plus and minus. So this picks that up, and you monitor it. But if you leave these terminals open, the pressure in there, the electrical pressure I was talking about, will build up until it can reach the amps that this ratio of turns to this one wire. It'll try to get to the voltage in order to produce the amount of current it needs, and it'll actually break the insulation down, but it can make thousands of volts, and these can kill you very quickly. Motors, we'll get to the motors now. We have two types of basic power. The DC, which is like what comes out of a battery. The current only flows in one direction. It's real simple. Alternating current's kind we get out of our outlets, wall sockets, and it's alternating. You have the plus and the minus. Every 60 times a second, that's reversing. Plus, minus, minus, plus, plus, minus, minus, plus. I mentioned before that those inductors resist changes. So switching back and forth, that inductor is constantly resisting that. So that's why you can have a very low, I don't know, you guys ever measured resistance on some big motors? They'll measure like a short circuit, like as if you were just measuring the wire. How can you put like 480 volts across the short without pulling if you looked at our formula before, that would make a lot of amps. And they do. When you first close it, they do make a very large amount of amperage. But you also have that inductive reactance factor where the coil resists that change. So as that current is alternating back and forth, that inductor's internally resisting those changes. Basic parts of a DC motor. We have brushes, which are just contactors. They're just to make contact. And a commutator, which is, you can see it's like a ring, but it's split. And each one of these would go to either set of coils. The rotating part in the center would be what we call the armature. Now, one of the parts they didn't list here is the stator here. These here would be they could be permanent magnets. I actually have one here. This is the stator of a DC motor, and you can see there's two magnets in here. A lot of times the big ones, they'll have an electromagnet, and there'll be a separate supply for what they call a field. Okay, the armature is the rotating part of a motor that includes the the main current carrying coil in which the force is created. And those are some pictures of some brushes. A lot of you guys probably changed those out before. They have springs on them so they maintain tension against the commutator so that it makes contact. That's the commutator here. And you can see it's a bunch of like plates separated by insulators. Okay, and this is basically how it works electrically. We've simplified the coil down to a single wire. I told you about the force going around it before. Well, if you got a battery, you hook it up to these brushes. These commutator contacts are connected to this wire. It doesn't show it very well, but this wire is connected to these commutator contacts here, back through this one. So you complete a circuit this way, flows that way. You know what happens when you put like a north and a north together in a magnet? They're going to push each other apart. And same way with the south and the south. So in this case, you have a north and a south, and one will attract it and the other one's going to push it away. So it'll force motion. Once you energize this coil, you have a south against south and south against north, one pulling, one pushing, causing it to rotate until this ring, now you notice it's split. Once it gets to the other side, it's gonna reverse it, and then so you're maintaining a magnetic difference so that positionally it's always pushing and pulling. So you get rotation constantly. Now this was a very simplified. It's only got two. If you look at that one that you pass around, it has many of them and many poles on it.
Does that help having more poles? Does that give you more horsepower?
Well, if you look on here, if you've only got two, it's going to push it to here, and then
you got to rely on inertia to keep it going.
Right. If you've got a whole bunch of these, then you can switch it as soon as it gets into the optimum position for push and pull. You know what I mean? So instead of it getting over here and inertia carrying it, you've got another one pushing again. You know.
So would that relate directly to more horsepower by the more number of combinations of that you have, or not necessarily?
Generally,
okay.
Yeah. It would definitely be more. It's more efficient the more poles you get, because you can get closer to that sweet spot. You know, the closer you are to here, the more power. You know, the magnets. The closer you get, you know, they get stronger and stronger the closer you get. So the more you can maintain this position of push, the closer to optimum. Yeah, the more efficient it's going to be. Okay. When electricity flows through the armature coil inside a magnetic field, the coil rotates continuously. When the coil rotates, the shaft attached to it also rotates. Thus, it is able to do mechanical work. I don't know if I'm going to get ahead of myself here or not, but I mentioned before, when you pass a magnetic field across a conductor, it'll also induce a current flow. That's like I said, if you pull the power off, that magnetic field collapsing induces current. Well, by rotating, if you rotate a coil in a magnetic field, it'll generate a current. So, yeah, it'll actually generate it. A lot of times in DC motors, they'll have the load will actually pull it faster than the motor can go, and it's actually acting as a brake. You know, it's if the load actually wants to pull it, so it's actually doing a reverse torque thing, and it'll actually regenerate back to the line. You'll actually produce your little hybrid cars do that too. Right, and she's got one of those little Prius cars. Like when you brake. If you don't brake too hard, I mean, if you brake too hard, they're going to engage the brake. But if you brake lightly, they're actually using the electric motor in there as a generator. It actually it's changing mechanical energy back to electrical energy, so it's storing it in the battery. So as you brake, you get to save up some of your power instead of wasting it as heat.
You hear the term regenerative drive on DC drives.
generally the speed is directly proportional to how much voltage you put on it, how much pressure you put on it. And the torque is proportional to how much current is flowing. So you can measure how much power basically by the current that's flowing through a DC motor. The thing about DC is when you first starting out, when you first start up a DC motor, it'll deliver you full torque right now. You know, AC motor don't do that. Yeah, the AC motor gives most torque when it's at speed, when it's at its designed speed. So some applications they need full torque at very low speed, and that's where you'd want to use a DC motor. They're getting better with the AC though, and they are able to generate a lot of torque at slow speed now, because of the technology of the variable frequency drives. So, okay, let me briefly go over AC motors. They're kind of backwards from the DC motor in that the rotational, the armature is still in the center, but the part that's doing the work, causing the motion is the stator, because on the AC motors, most of them, if you guys can see this, the stator is wound. You know, you saw the other one. It's got the permanent magnets in there. Well, in this one we have electromagnets. Basically, each one of these is an electromagnet, and when you put alternating current in there, you're going to have a bunch of magnets flipping back and forth, and that's so basically you got a field rotating around in here from all these magnets flipping over and over, and it drags this armature along with it. Now this isn't a very good example. Usually you can see the poles in here, but they got this one shielded. This actually has individual conductors through it. Now, the way an AC motor develops torque is that rotating magnetic field in that stator that drags it around. Each one of these conductors, and I told you when magnetic field crosses a conductor, it induces a current into it. As it induces a current, it produces its own magnetic field. So it has an induced magnetic field, and that develops the torque. But it actually has the rotating magnetic field actually has to be going a little bit faster than this, because it has to cross these poles to generate. So and they call that slip, because this isn't never going as fast as that rotating. They call that slip. One that has 4 poles on it, a motor that has 4 sets of poles, runs at synchronous, it would be 1800 RPM. But in order for this to generate torque, it has to slip past those magnetic fields and develop its own magnetic field, so that it has something to push against. So they call that slip. So they usually run about 1750, something like that.